Ok, excelente. Muy bien. Entonces ya podemos iniciar. Bueno, antes que nada, muchísimas gracias a nuestro ponente del día de hoy, que es David Romero. Excelente. Y sean todos bienvenidos a nuestros seminarios. Ya podemos iniciar. Antes que nada, muchísimas gracias a nuestro ponente del día de hoy. Okay. Ok, perdón, es que me estaba escuchando en la repetición de Héctor. Muchas gracias, Héctor, por mutearte. Pensé que ya estabas empezando, David. Me asusté, dije yo, espérame, David. Bueno, sean todos bienvenidos al Seminario de Fronteras de la Energía, nuestro seminario institucional semanal. Y el día de hoy contamos con la presencia de nuestro ponente David Romero, que trabaja en el laboratorio Atoms en la Universidad de Toronto. Y el tema que nos va a estar presentando el día de hoy se llama Physics-Based, Physics-Informed and Data-Driven Methods for Wind Farm Layout Optimization and Control. Nuestro ponente habla muy bien español, sin embargo, va a ser el seminario en inglés. Una, también porque vamos a tener invitados internacionales, y dos, porque pues, todo su desarrollo académico lo ha hecho en el extranjero. Entonces, déjenme presentar brevemente a David. David Romero is currently a Senior Research Associate at the University of Toronto, Department of Mechanics and Industrial Engineering. David holds an undergraduate mechanical engineering degree from Universidad del Zulia in Venezuela, as well as a master degree and PhD degrees in mechanical engineering from Carnegie Mellon University. Prior to joining the University of Toronto, he was an associate professor in mechanical engineering at the Universidad del Zulia, Venezuela. David's research interests are in the intersection of applied computing, statistics, and mathematics in support of engineering design, modeling, and optimization, particularly in the thermal fluid sciences. Current focus areas include AI-based algorithms for global optimization, modeling, and optimization of renewable energy systems, cardiovascular biomechanics, and tissue engineering. So it's my pleasure to introduce you, and please, David, if you want to share your screen.
Okay, let's do that right now. Okay, I think you should be seeing my slides projected.
Okay, we can see your share screen. Okay. So thank you very much.
Okay, well, thank you very much for the invitation to speak today to you. It's an honor to be part of this seminar, which I would like to be able to attend in the future to learn about all the interesting research that you guys are exposed to. As Carlos mentioned, my topic today is physics-based, physics-informed, and data-driven methods for wind farm layout optimization and control. The idea today is to go a bit over the work that our lab has done over the last few years. So it's a bit of a summary of previous work and some description of current focus areas. In terms of previous work, we'll talk about physics-based models and optimization, which has been our work until probably a couple of years ago, and more recent work in data-driven and physics-informed neural networks that we're using for this application. So I don't know how many presentations you have seen about wind farms, but this is the picture that everyone has to show. It's mandatory now. It clearly depicts the wake structures that form behind wind turbines, and it's I think an amazing picture to understand the effects we're talking about. And given a wind resource, for example, for this farm, you can see that depending on the wind direction, the energy production of the farm decreases significantly. In the worst wind directions, which are indicated with the arrows there, you get to produce about 60% of the maximum that the site could offer. And of course, that improves for other directions. And this gives an idea of the importance of designing the layout for the wind resource. And we'll see later, also considering the terrain features that affect the atmospheric flow. So we'll go a little bit over that today. Another important aspect on wind farm layout optimization is consideration of land land use constraints and environmental impact, which play a significant role in industrial practice. Not so much in research work, not typically considered, but there are many restrictions to where the turbines can be placed within a given terrain, and also terrain features will affect the flow, and that also has to be taken into account. As an example, this information is for a jurisdiction like Ontario in Canada. You're required to place turbines 500 meters away from any human dwelling. So if the wind farm area was supposed to be the white rectangles, now the gray out areas are no-go places for wind turbines. You have to keep a buffer of 250 meters from roads, 150 meters from electrical transmission lines, and 60 meters from the lake shores. So once you consider all these restrictions, then instead of placing turbines anywhere, you can only place them in the areas that are colored here in this image. And this makes what an optimal layout is less obvious, more difficult to obtain for sure. So informed by our collaborations with an industrial partner that actually designs and commissions wind farms, we decided to tackle this problem a while ago. So generally weight losses can be 10 to 30% decrease in annual energy production. Designing the layouts and infrastructure is a complex task, and there are many considerations to be taken. And what we saw was that the literature only dealt with energy generation, but ignored other type of constraints. So that's why we decided to take a look at this area. So in the first part of the presentation, the optimization work we're going to see is based on what are called kinematic wave models. Basically, if you look at the picture on the top right, that's the picture, a top view of a turbine with the incoming wind flow and sort of what the wake region is supposed to be and the effect it has on the flow. So these models have different levels of using conservation of mass and conservation of momentum to try to come up with analytical expression for what the wind speed is behind the turbine and how it recovers. The simplest model is the one shown here. It's a Jensen model, considers a linearly expanding wake and focuses only on mass conservation. And the prediction of this model is what you see in the blue line in the plot in the bottom right. Basically, for whatever free stream wind velocity you have, once you hit the turbine, it decreases significantly, about 60%, and then it recovers following that pattern. And the horizontal axis is a non-dimensional distance, counting the turbine rotor diameter. So you can see that about 20 turbine diameters away, which could be up to 2 kilometers for the biggest turbines, you get 90-something% recovery. But this model is only valid in flat terrains, and it has significant assumptions, but it has been used a lot in the literature and in industrial practice because it's simple to evaluate, and it gives, for something so simple, it gives reasonable results. You will see error levels in a future slide. The other aspect is once we have a turbine that is in the wake of several upstream turbines, we have to find a way of combining the effect of multiple turbines upstream. And many options for that too, shown here in this slide, but the most common one is also the most accurate is the sum of kinetic energy deficits, which is the third expression. Using that, you end up with a behavior like the one shown in the bottom plot, in which after each turbine you have a decrease in the wind speed. That decrease is less and less the further turbines you get. And after the last one, you get a full recovery eventually after 40 or 50 diameters. So these two tools, the single wake model and the wake combination model, is what a lot of people have used for research work in wind farm optimization. And that's also the basis for the first part of our work. So in this space, we focus on problem formulations and algorithms for solution. And we first look at meteoristics, like genetic algorithms, those kind of nature mimicking algorithms. for different type of formulations, considering the turbine locations as continuous variables or as discrete variables, and considering land use constraints or environmental impacts, different ways of formulating the problem to try to characterize really what we're dealing with. We also use formal methods for mathematical programming, which come from the operations research community, mixed integer linear programs and quadratic integer programs, based on approximate formulation of the problem that we created, and that was suitable for large-scale optimization. And finally, we look at nonlinear programming, gradient-based approaches, which surprisingly nobody had done before. I don't think we're going to have time in this presentation to take a look at that, but we have a publication that is available if you're interested. So to set up the stage, this is the typical work, and this was the key reference up until, I don't know, 2010 or something like that. The works by Mossetti and Grady. They consider basically a wind farm, a rectangular or square domain, like the one in the top figure. And turbines are allowed to be placed only in the center of those squares. So it becomes a discrete variable problem. And then they solve this problem with genetic algorithms. The objective function for that optimization was to reduce, is in the bottom left, a combination of the total power produced and the cost per unit power. And results are like the ones shown in the bottom right by Mossetti and Grady, about 10 years apart. You see different results, very different layouts, because this problem in particular, when you set up 30 turbines in a wind farm that is discretized into 100 squares, there are many optimal solutions that are equivalent, and you are seeing two of those here. Intuitively, we will have designed the Grady layout, but the Mossetti layout has an equivalent energy production, so this is compatible. So we took this problem and then we expanded it to make it multi-objective, considering now one of the effects of environmental impact, particularly noise generation. On the top right, you see predictions for a given layout of what the velocity field will look like and what the sound pressure level map is. Sound pressure level is predicted using ISO standard method of calculation, and that is using sort of regulatory work for this purpose. And energy generation is the Jensen model with the sum of kinetic energy deficit. So the expressions for the two objectives are there in the slide. And then the sound pressure is measured at a series of receptors, noise receptors, which are the red dots on the bottom left. That's the wind farm domain. 7 turbines are shown there, and then we are maximizing the energy production of those turbines and minimizing the average noise on the red dots on that domain. That's sort of the optimization problem. And we solved that for many number of turbines for different wind regimes. A typical result is what you see in the bottom right. It's a Pareto set of solutions. Typical for multi-objective problems, we don't get one solution, we get a set of non-dominated solutions. And please note that the horizontal axis, which is energy production, is reversed. So the better layouts are towards the left. So let's look a bit in detail into what that kind of result can tell us. So here we have 2 Pareto sets for 2 different number of turbines, 25 and 28, on a given terrain. And basically in this map, every dot is the energy production and noise level of a layout. Whatever that layout is, we don't see it here. We see the result in terms of energy and noise. And this gives us a lot of information because this curve is basically telling us what that specific site with that specific wind resource and that specific type of turbine can give us. What are the possibilities? Once we decide we're going to place a certain number of turbines, this is what we can achieve, basically. So it's a very useful information in terms of design. It also has a nice interpretation. For example, If we make this comparison along the blue line, that's how much extra energy we're going to get per year if we add 3 more turbines without increasing the noise level, for example. And we can make these kind of comparisons for different number of turbines or noise levels. And also a rough interpretation, more kind of intuitive, not necessarily mathematically perfectly sound, is to look at this sensitivity, because the slope of these lines tell us what's the price of the noise regulation. Basically, we can look at the red line and the top, and we get the idea that for each decibel of noise that we are allowed to accept, we gain 0.05 gigawatts hour of energy. And that's really indicating the trade-off between energy and noise in this site. And because energy has a price, it also gives us the price of the regulation. So it allows us to look at regulation in an economic context as well, not only in terms of pollution. So then to this problem, we decided to add the land use constraints. So one example is what we have here in the bottom left. That's a wind turbine area, rectangular. And the red regions are places in which we are not allowed to place turbines, because those are dwellings. And those are the setbacks from each dwelling. So example of the results we get are in the right. We can look at, for example, that's a figure C, in which we are in this terrain placing 15 turbines. And the parameter phi, it indicates the percentage area that is usable from that terrain. And we can easily see as much more area is available for us, we are able to achieve larger energy productions with lower noise levels at the receptors. So again, important information for design and also regulation. And one additional aspect is that from the point of view of the wind farm developer, a plot like this can indicate how important can be a certain area in the wind farm in terms of achieving an economic objective. So that also puts a price on the negotiation for that contract for land use. So our industrial partner was very happy about this type of representation and messaging that we could get just for solving an optimization problem with enough of the sort of context that really happens in industry. So in terms of our work in this area, we consider multiple optimization formulations, constrained, unconstrained, multi-objective, single objective. For multi-objective cases, we use genetic algorithms and meteoristic, both for the constrained and unconstrained formulations. We didn't show here, or I didn't show here, the mathematical programming approaches, but those were very successful because the methods they have in operations research can put a theoretical bound on how far we are away from the optimum. And there's also a valuable information because meteoristics don't have a guarantee of convergence. These methods, even if they don't converge, they tell us how far we are from the solution, which is also very useful. And finally, also not shown here, we did gradient-based models. If you think about the wake model and wake combination models I showed you at the beginning of the presentation, they are analytical expressions. Surprisingly, nobody had bothered to try to obtain closed form derivatives and gradients for those expressions with respect to their coordinates. So that's something that we set out to do. Slight modifications in terms of how the wake propagates to make it a continuous problem. And we were able to successfully solve the problem actually very quickly, very efficiently with these methods. So interesting results, publications out of this, but the problem is that these models can yield 10, 15, 20% errors in terms of energy production calculations and only work on flat terrains. So for more common applications that have terrains that have certain complexity or certain features, we require CFD. So then we set up to work on wind farm optimization based on CFD models. And this is an example of a terrain that's sort of minor complexity still has some hills there that will definitely affect the flow structures and wake propagation. And we have nearby a mountain that will also be a terrain feature, important in terms of characterizing the wind resource in the site and how the wakes are going to propagate. So for the CFD setup, we obviously have the option of modeling all the turbines in all their complexity, considering the rotors and using rotating multiple frames for the simulation, very complex simulations. If we want to get all the details of how the wakes generate and all the turbulence and eddies and everything. But for the purpose of optimization, better option is to use an actuator disk model in which the turbine is not represented in geometrically faithfully, but instead replaced by a momentum sink that is basically a disk. And that basically has the same overall effect on the flow, but it doesn't have the details of the dynamics of the wake. Very useful for the purpose of optimization. Still, even in that case, the domains for simulation are really large. So the figure in the bottom, that is kind of purple and pink and red, you see a little shadow in the top part of that box. That's an actuator disk representing a turbine. That gives an idea of the scale. So that turbine rotor is 80 meters. So you can imagine the size of this domain, and this is just to simulate a single turbine. If you have a farm, you have huge domains with many millions of cells. We're talking about 3D, turbulent flow. So computationally expensive simulations. So even though we can do simulations, and we did a study comparing turbulence models to see which models were more accurate with respect to available field data from real wind farms, still it's very computationally demanding. So for the purpose of optimization, we needed special approaches. So for this application, we look at the adjoint method. Commonly used in aerospace applications, but it's just a method to calculate the derivatives of the field variables with respect to some design parameters that may be part of boundary conditions or short terms or geometry or whatever it is. So the way it works is that if you were to optimize a functional of the field variables, here phi represents, for example, the speed, streamwise and cross-stream and vertical wind speeds, and alpha maybe some design parameters like the location of the turbines. So if we're going to optimize a functional of the field variables, for example, the annual energy production, which is an integral of the speeds over a year, subject to some constraints, and those constraints, G of phi and alpha is basically an Navier-Stokes equations. To calculate the gradient, we could use a finite difference approach. Do a simulation with the turbines in one place, move one of them a little bit, and calculate and get an estimate of the gradient, and do that with all the turbines. So we end up with a lot of CFD simulations just to calculate one gradient. So that's really not a feasible approach for optimization. The adjoint method allows us to compute the gradient with much fewer evaluations because it makes the gradient independent of the number of variables that we need to calculate the gradient for. And the computational cost for that is the equivalent of an additional CFD simulation. So for the price of 2 CFD simulations, we can get the gradient. That would take 41 simulations if we use finite difference approach. So for the joint method, I'm not going to go into details. The formulation are quite complex. I'll show you an example of an equation coming out of it that is a bit scary. But the idea is that you, instead of having the optimization problem as maximizing that functional, subject to the constraint of the partial differential equations, G, you write it as a non-constrained problem using the method of Lagrange multipliers. You have the functional plus some term multiplying your constraint violations. And these constants here, these variables, are called the adjoint variables. So there is a nice mathematical trick that allows us to calculate that gradient, because G is 0, because those are the physical laws that the system has to meet. So that has to be 0. And that means that we can choose the adjoint variables to be whatever we want. But with a very specific choice of adjoint variables, specifically if we choose the adjoint variables so that they satisfy the second equation from the bottom, then we can cancel out a lot of the terms in the gradient expression and are able to calculate the gradient easily. This method, this formulation, has to be particularized for the system that we are applying it to. So if G is actually the 3D Navier-Stokes in turbulent flow, and J is the annual energy production, and we try to do that, we end up with scary equations like this. These are all integrals of PD-looking expressions. There's a bunch of partial derivatives and products there. What we did was to do this derivation, which was very painful, and we implemented those equations in OpenFOAM, creating a custom solver so that we can calculate the adjoint variables and then calculate the gradients. And then we link that with an quasi-Newton optimization method. We apply that, of course, to certain validation cases, but more interesting is this wind farm in Norway. This is a real wind farm for which data is available, including the coordinates of the turbines. So we got the terrain details from Google Earth. We have the coordinates of the turbines, which are indicated in subfigure B. And we have the wind resource, which is on the top right. Then the actual layout of the farm, this is an existing wind farm, is on the bottom left. So we did that simulation to see how much energy we are estimating it will produce. And then we ran the optimization using 3D turbulent flow simulations on this terrain with the adjoint method to calculate the gradients, and we did the optimization. And we end up with the ultimate layout shown in the bottom middle figure. If you look closely, very few differences can be seen. They look similar enough. So the next figure that has red dots and blue boxes indicates how much the turbines move during the optimization. So the initial positions are in red, that's the original layout. And we track there where those turbines move during optimization to find an optimal layout. And just by doing that, we can show that the optimal layout is 6%, will produce 6% more annual energy, which is a significant amount of money in terms of production for basically the same wind farm with just minor variations. And that's achieved only by moving the turbines a little bit. Some turbines barely move 30 or 40 meters, like turbine 1, for example. But some turbines move about 250 meters or so. And with those changes that take advantage of the terrain features, was sufficient to, in theory, produce much more energy. Now, this is done with, this is based on a CFD model that was validated against wind farm data. So it's reasonably accurate. So I'm confident on this type of results. Although, of course, as everything in engineering and modeling, you have to take the results with a little bit of grain of salt. You will need some certainty predictions around that, but it is a significant improvement. So in terms of CFD models and adjoint methods, we then, basically summarizing, we proposed this method to do the CFD simulations. We validated those against field data, and then we implemented your method to do optimization. It works well, but computational cost is definitely an issue. Of course, if you are designing a wind farm, that's a one-time thing done at the beginning of the project. So it justifies the cost for an optimization. But if you start adding additional considerations in terms of infrastructure, or you're going to consider the structural coupling, aerodynamic structural coupling, or considerations of accumulated damage and lifetime, then computational cost is going to increase dramatically. which means these type of models, which are the most accurate, are not really suitable for control once the wind farm is in place. So that was a motivation to look into methods then to do this kind of predictions much faster, but still accurate. And that got us to machine learning methods. Here, physics-informed, data-driven. So there is a very large literature on surrogate models, meta models used for design optimization. That's common in mechanical engineering, aerospace engineering, and many engineering disciplines. If you look at the literature, you will see this kind of efforts in which you have a system that you design with a computationally complex model, computationally costly, and you do that by deciding a simulation campaign. You design a computational experiment, you run a selected few simulations, then use that data to feed a model that guides your design process, eventually confirming your results with the simulation model itself. The idea is that it reduces the total number of model evaluations and thus reduces the cost and time needed to reach a design decision. Many methods have been used for surrogate models, from quadratic polynomials in the response option methodology to Gaussian processes, which are probably the most common, and of course neural networks. Neural networks were used for a long while until the 80s, then fell out of fashion. And obviously, as everyone has heard by now, they are definitely in fashion now and being used a lot. So an attractive thing about neural networks, they're universal approximators, given the architecture has enough capacity, meaning enough internal units, and you have enough data to train them. And they can reproduce any nonlinear function. An example of a neural network is shown there in the figure. You have some input units that basically pass on the data, in this case, coordinates, spatial temporal coordinates, up to processing units, which are the blue circles, that basically takes linear combinations of those data coming from the previous layer and apply a nonlinear transformation to them and forward them to the next layer. So this composition of simple operations of linear combination and nonlinear transformation end up having a large capacity to approximate any function. And typically you calculate the coefficients of those combinations, and they're called the weights of the network based on data by a nonlinear regression problem. You're basically optimizing the residual, minimizing the residual to find the weights of the network. So an important development, and probably 8 years ago or so, is the physics-informed neural networks, in which as part of the objective function that is minimized to train the network, we include residuals of the governing equations, Navier-Stokes, continuity, or whatever it is. And that means that the network is finding the weights that best fit the data while also complying with the physical laws. So it improves prediction capability a lot, allowing lower errors or better accuracy with fewer data samples. So they had shown good success for several classes of PD governed systems, but are very difficult to train. To be honest, we gave it a shot, and many people have reported this. In principle, the idea is sound, but when you implement it, it's not as easy to really obtain the network that gives good predictions. So in this context, image-based architectures are also relevant, and people hadn't really looked at them before because they are for object recognition, computer vision, those kind of applications. But as engineers, we do simulations and we make decisions based on simulation results we see as an image on a screen. So these type of architectures are also relevant for generating those images from data. Right? So we decided to take a look at that. We ended up designing a network architecture like the one shown in the figure on the left. It follows an encoder-decoder pattern, which means on the top left, we take an image of the turbine layout. At this size might not be easy to see, but you have a black square with some white dots, which indicate the position of the turbines. And you also have a representation of the incoming wind velocity, the free stream velocity, which is that red square there. You take those as input, and then through a series of convolutions and dense blocks and encoding blocks, you do nonlinear transformations of those images and reduce their resolution, reduce their size by combining pixels. And you do that in many layers, the number of layers to be decided, until you end up with a small subset of what are basically variables. So basically you are finding a nonlinear mapping between the input to a certain space. And then from that space, you do the predictions by expanding that representation again into the original size through the lower route in that figure, which is a series of the coding and dense blocks operations that end up giving you the flow field of the turbines in this case. Just for reference, in the figure, there are some details of how the dense blocks and encoding blocks do those operations, but it's the same idea of the networks. You will do linear combinations and nonlinear transformations of the variables and pass that information along. So this architecture, we decided to test first with analytical models. Basically, we take the Jensen model that we use in the first part of the presentation, and also a similar model that is based on Gaussian wakes, has a little better prediction accuracy to generate a lot of images of turbine layouts and the corresponding flow field. And we also generate data using the CFD model, in this case in 2D, just for the sake of illustrating the capabilities of the methodology. So we generate a lot of random layouts with random number of turbines between 10 and 30 and random inlet velocities. So based on this data set, which is a bunch of images of simulation results, we train the network. And the important part here is the loss function that we use. So training the network means minimizing the loss function, shown in top right, to find the weights that sort of indicate what operations the network does. And what we did was not only reduce the error with respect to the data, but also error with respect to the annual energy production prediction from that data. The idea here was to give a bit more emphasis to the importance of being accurate in the area surrounding the turbine, which is a critical thing to predict the energy production. And then because we were doing this sort of for the first time, we took good care in characterizing the performance of the method. So we play with those relative weights of the two terms, error in predicting the speeds and error in predicting power. And we obtain something like what you see in the slide. In black is the error in predicting power as a function of the weight that that term has. Obviously, if that weight becomes 1, you are basically optimizing the network to predict power and your error is very small. When that weight is 0, you're optimizing the network just to predict the whole flow field. And that also results in small errors in speed, and I would say acceptable errors in predicting power. But there is a behavior there that is worth mentioning, which is if we weight the power errors too high, above 0.8, then the errors become much larger. So that gives us information about how to weight, give relative weight to the two terms while training the network. With that weight choice of 0.8 for the power term, we then characterize the performance of the method in terms of the effect of the resolution of the images. Remember, we generated flow fields randomly, and those are encoded as images that of different resolutions. The resolution may be important. And also how much data do we need to train the network. And we get this kind of curves. On the left is the curve corresponding to a baseline architecture that was used for a different problem, but mathematically similar. by other authors, and on the right, the network we designed for this application. And I guess the important take-home message is that the architecture we propose is less sensitive to image resolution. That can be seen by the error bars around the plots. And it's also less sensitive to the data set size. So it can achieve similar prediction errors with fewer data. So for example, as low as 64 2D simulations are enough to reach a speed error of about 2%. So we find that to be a reasonable result in terms of potential applications. And then we explore an important part, which is this approach of using neural networks allows us to integrate data from different models. For example, you could use data from analytical models like Jensen and data from CFD models together to train a network that will be more accurate than just an analytical model. So integrating sources with different levels of fidelity, it's something that these networks can do well. So we try here several ways of doing that. One option is that the warm start, in which we train a network with analytical model data, and then use the weights of that network to retrain the network for CFD data. So those are the initial weights for the training of the CFD data. And the weight transfer approach, we train the network with analytical data and then freeze those weights and only retrain with CFD data the first and last layers of the network. And in the model fusion strategy, we basically take the analytical model prediction as an additional input to the network. And we train the network only with CFD data. Our tests show that the model fusion strategy is the best one to try. Basically, we use 64 or 128 simulation results to train a network that takes an input, the layout, and what the analytical model will predict that layout would do. And basically, the network corrects that information with what it learned from the CFD data. Not only we achieve very low errors for prediction speed and power, but an important aspect is that the rank correlation between the predictions is 95%. That means that the predictions preserve the order of the solutions. If you were to sort them out by their power production, the neural network model will sort them out correctly 95% of the time, which means the model can be used for optimization, because optimization is really about relative ranking of solutions. So we were very happy with the results in this case. So that takes us to what we have published so far. Current work, we are now training networks to predict different components of velocity. So now we're predicting not only the stringwise, but also the span-wise velocities based on analytical models that can give us what and CFD simulations. And our initial tests show that when we train a model using both components, we get much better prediction results. This figure shows what a cross-section of a flow field will be. So that line A prime, if we take a cross-section of the flow field there, we can see that the blue line will be what an analytical model would predict, the Larsen model. The black line is what the CFD result will say, and the red line is what our neural network model says the speed profile is. So as you see, very accurate results with only a few simulations. And the results of the network can then be used, the trained network can be used to predict behavior of any layout. We're also working on now using or incorporating the effect of yaw angle, which is the angle between the turbine and the incoming flow field, and adding physics to the networks in terms of the continuity equation and Navier-Stokes to obtain sort of accurate results. And you can see in the figures there the comparison between the CFD results, which we are considering true for this purpose, and what the neural network model predicts, which is indicated in blue here. As you see, for different yaw angles at different positions behind the turbine, we're predicting the cross-section of the velocity field rather well. And this opens up the possibility of applications for weight control, because these models, once trained, they run in microseconds, milliseconds. Is really an accurate and fast prediction. So this is the type of work we're focusing on now. So sort of to close up and summarize what we have presented, we started in the first part of the presentation with work based on or focus on the optimization of the far layout using analytically based models for wake prediction. And we focus really on understanding how the different formulations behave and what kind of algorithms are good for solving them. Then we move on to problems in complex terrains, which require CFD methods. So we develop those CFD models, characterize their accuracy with respect to field data, and then use them in the context of the joint method to optimize based on what are really the best prediction models for this application. And more recently, we have been focusing on neural networks, machine learning applications. So we can do these predictions as accurate but faster to enable real-time control. And with that, we'll conclude my talk. And if you have any questions, I will be more than happy to answer in English or Spanish.
Thank you very much for opening the opportunity to ask you questions in to ask you in Spanish. So if there is people here that want to have some doubts or something, wants to comment about the presentation, you can do it on Spanish if you want to. You can do it. So I think there is no questions yet, but I'm curious about. Let me see. Diego Arturo Canul Reyes asks, how does the duration of the wind field time series used as input data affect the performance of the optimization models you presented? Do you use any methodologies such as PCA to capture decisional or general variability of wind resources more efficiently?
Sorry, can you repeat that, please?
Okay, I think the first question. First, the wind field time series used as input data affect the performance of the optimization models you presented?
Okay, that's so answering that, it wouldn't. We start from a statistical distribution of the wind, which is typically measured on site and correlated with other atmospheric models, and it's given as a wind rose. So we have probability distribution for wind speed and direction, and that's what is used to evaluate the annual energy production. From the point of view of the model, we don't use that. We focus on the model based on a single speed direction, and then that model can be sort of evaluated for different rotations of the layout. And then using the probability distribution, we calculate the expected value of annual energy production, which is what we really use. So basically, we focus on the building block, which is a single model for a given wind speed direction. And then, as needed, we rotate the layout and use the same approach to calculate what happens at different angles and then sort of integrate that probability distribution.
Okay, thank you. And the second one is, do you use any methodologies such as PCA to capture the seasonal or diurnal variability of wind resource more efficiently?
No, in our case, we don't, because that's related to the wind resource, which we assume as an input. Where we focus on the model that will do prediction for a single wind scenario, and then use that to calculate the expected value based on the given probability distribution.
Okay, thank you very much. I don't know if there is any doubts or questions. I have one. You use the actuator this model, which is, I assume, is only the actual momentum model, right? Where you just incorporate the information about the wind turbine in the thrust coefficient, right?
Yes.
So my doubt is about the how do you calculate or how you estimate the sound pressure level if you need information about the profile? I assume that you include only the aerodynamic noise emission, right, for a wind turbine. The mechanical is internal of in the nacelle is not taking into account only the aerodynamic part. So
Yeah.
how do you include that? Yes.
So there are curves of noise levels for the different speeds of the turbine that the manufacturers can provide.
Okay. Yeah.
And we use those just as we use a power curve. There is
Yes.
a noise emission curve. I'm not
Yes.
sure if they include all sources of noise, aerodynamic and mechanical. I'm not sure.
Yes.
I
Yes.
would assume because of, it's a commercial technology, I would assume there is a standard for measuring them.
Yes. Yes.
I will consider those sources.
Yes, I forgot that the manufacturer usually shares that kind of information about the noise levels for each speed. And well, there is no question yet, so I have I have a very few. The other part is about the lay optimization is before the wind farm is installed, right?
Yeah.
Because in the last slides you mentioned about the geo angle. So,
Yeah.
for example, how could change the the validation, or for example, if you have already installed the Winterman fine layout,
Yeah.
how the geo angle could beneficiate
So the way it works is that the optimization is done assuming that the wind turbine is going to be completely orthogonal to the
yes.
wind direction, right?
Yes.
And that's an aspect that we also plan to evaluate. But the turbines can rotate to face the wind, and
Yes.
there is a control for that.
Yes.
The thing is that, surprisingly, the maximum energy production does not necessarily happen when they are completely orthogonal. When you look at it at the wind farm level. For an individual turbine, of course, but if you have many turbines for certain wind directions, you have certain wakes, and then by drawing the turbine, you can redirect that wake away from downstream turbines in a way that compensates whatever energy you're losing for not being orthogonal to the wind.
Yes, wake Mendeleev, right?
From the wind farm perspective, controlling the jaw of individual turbines, it makes a lot of sense, and it's actually done.
Yes.
It's a matter of how well can you predict what's going to happen, and how you do that.
It's nice. And the other one is in the CFD models, that when you talk about the complex the complex terrain, you what type of initial conditions you include in the inlet? What is the inlet condition? Is a mature one, or is a profile? What do you include there?
So there is an atmospheric boundary layer model that provides a speed profile versus height. It's kind of logarithmic. I don't remember exactly what the expression is right now, but it looks like a kind of logarithmic profile. So we use that for the site, and there are also expressions to estimate the turbulence intensity that comes in the farm. And then, of course, the bottom is a no-slip condition, and you make the domain large enough so that on the sides you can impose zero gradient conditions, and it will be fine.
Yes.
And at the top, the speed you set to whatever was the speed in the uppermost layer. So basically, that's
free boundary condition.
That wind just goes undisturbed at the very top of the domain. That's how it's set up.
But it's a RANS model, it's a less model. What type of
It's a RANS model.
RANS model.
We haven't gone into less or DNS. It's just too computationally expensive.
And is epsilon perhaps, or omega?
This one is SST cap omega. We tested different versions of these models against field data, and the SST cap omega came much better than the rest. We also tweak the constants. We get much better results for that. But then, from the point of view of publication, that might be a bit controversial. So we stay with the standard constants and publish everything with those.
Yeah, that's is the one thing that bothers me about the RANS models, because all the I forgot the wall models, you have to turn, or you have to select the millions out there. There is millions out there, so you have to pick one that fits your.
And for this case, wind farms, there were different papers arguing for different models. So we were going to do the adjoint, and we said, okay, we first have to sort of make a decision here, and we decided to test all of ourselves with 3 wind farms for which there is openly available data. That's basically what we did.
Yeah, but you have a bigger problem that make your your model, the machine learning model works, right? Okay, this is another question. Is how much different will the modeling process be for offshore wind farms layouts compared to onshore farms? That's the first.
From our point of view, there will be no difference at all. Certainly offshore, the sort of terrain is rather flat. The sort of ground effects are different, but that's an input to what we do. So it really doesn't affect our approach or protocol or workflow.
Okay, there's another one from Diego Canul. What additional variables or considerations, such as sea conditions, foundation types, or marine ecosystems, should be taken into account? I think it's close to the offshore one.
Different modeling process for sure. Additional variable considerations, sea conditions. Yeah, basically, so far we have done this only for the flow field. We are starting the process of now including structural considerations and models for damage, because in reality, that's a major theme for wind farms. Yes, they want to produce energy, but they have maintenance costs, and they actively control the farm to avoid certain wake scenarios that they consider damaging. So we are trying to incorporate those in the model so we can better work at the control part.
Okay, thank you very much. I don't know if Diego is happy with that, or wants to add a little bit more. I am curious about the couple between your machine learning model or with CFD, because you have to have a lot of CFD data, right? And the CFD data by itself takes a long to finish, right? And what is the process? Because let me just focus about the Reynolds number, where you have a lot of Reynolds situations happening in a wind farm layout, right?
Yeah.
And just the Reynolds, the atmospheric Reynolds, not the one who is relative to the wind turbine rotor plane, right? And how do you manage to control that? Because you have a diverse situations occurring in a wind farm. So how do you manage the big data and the big
so the data so far is not as big as you would think. We're talking we have been doing tests with 200 300 simulations, which certainly not for your laptop, but not terrible. And we have explored different ways. In our initial efforts, we were working with normalized flow fields, so that we would remove that effect. But we decided to incorporate the speed at the scale it is. So it's unnormalized flow fields. We basically have to generate simulations for the same layout with different speeds, and of course for different layouts. So as long as our data set has enough of the variety that it needs to have, then we're able to capture. Of course, we're still working on this, but based on results we have had in the 2D case and with image-based approaches, not a lot of data is needed, not as you would think. For the purpose of controlling wakes here. Of course, we are not modeling all the details of the wakes. It's an actuator this model, not an actuator line model.
Yes.
Or not the full geometry, which will require certainly much more
Sí.
data to be able to capture.
Yes.
So we took away some of the complexity of the problem that way, and we think it's still meaningful for the application we have in mind.
Okay, nice. Thank you very much, David. I think there is no more question in here, and I think also in YouTube there is no more questions. Let me turn to Spanish. Quiero agradecerte la oportunidad de que hayas presentado aquí. La verdad es un trabajo muy interesante y creo que está ahorita como en auge, ¿no? Entonces creo que esta información es bastante
No,
bueno.
mira, muchas gracias a ustedes por la invitación. Por supuesto, como researcher, tú sabes que siempre queremos hablar de esto con quien se nos ponga.
Sí, claro.
Realmente me da mucho gusto poderse presentar a ustedes en México, dado mi background, pero en general, en el contexto de investigación, de poder hablar de esto, ¿no? Y bueno, tiene una serie de seminarios que ya lleva un año andando, por lo que me dice.
Sí.
Mira, si me puedes anotar en la lista de distribución, sería ideal para poder ver qué otras cosas les presentan a ustedes, para estar un poco también
Excelente.
en contacto.
Excelente. Sí, claro. Y sí me gustaría platicar un poquito más de esto. Creo que tenemos un amigo en común que es Nafis, entonces sería interesantísimo, sería interesantísimo a ver en qué nos podemos ayudar. Sabemos hacer la parte de CFD, estamos aprendiendo a hacer eso, entonces creo que tendríamos ahí una colaboración bastante interesante. Entonces, bueno, pues muchísimas gracias, David, y muchas gracias a todos.
Gracias, Carlos. Hasta luego.
Ajá, estamos en contacto.
Dale,
Nos vemos.
chao. Hasta luego.